Now let us see the specific heat capacity and the molar specific heat capacity. The heat capacity of any object is given by the amount of heat required to raise the temperature of body by 1 degree. So C is equal to delta Q by delta T. The SI unit of heat capacity is Joule per Kelvin. The heat capacity of any body depends on the material as well as the size or mass of the object. If we want to make it independent of the dimension or independent of size, then we should divide it with mass. So the specific heat capacity is the amount of heat energy required to rise the temperature of body by 1 degree per unit mass. So we can write the specific heat capacity capital C as Q upon M delta T. As we have divided this with mass, it will independent of mass. So it is the only characteristic of material. The SI unit of specific heat capacity is Joule per kg Kelvin. The molar specific heat. The amount of heat required to rise the temperature by 1 degree for 1 mole. Then it is the molar specific heat. It is denoted by C dash. C dash will be equal to delta Q upon mu delta T. Here mu is the number of moles. The SI unit of the molar specific heat is Joule per mole Kelvin. Now let us see the specific heat capacity of water. Initially, heat was measured in calorie only. Earlier, it was defined as the amount of heat required to rise the temperature of 1 gram of water by 1 degree Celsius. But with the advancement in thermodynamics, when more precise measurements were taken, it was observed that specific heat of water varies slightly with temperature. So, to define calorie more precisely, it was necessary to specify the unit temperature interval, GEM. Then finally, we may define 1 calorie as the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. That is equals to 1 calorie. Since the SI unit of energy is Joule and heat is a form of energy, so it is preferable to use the unit Joule. So in SI unit, the specific heat capacity of water is 4186 Joule per kg Kelvin. That is equals to 4.186 Joule per gram Kelvin. The specific heat capacity depends on the process. Or the conditions under which the heat transfer takes place. For gases, two types of specific heats are specified, that are CV, that is specific heat at constant volume, and CP, that is specific heat at constant pressure. For gases, an ideal gas, the relation between Cp and Cv is Cp minus Cv is equals to R, where R is the universal gas constant. So let us prove how we can write the Cp minus Cv is equals to R. From the first law of thermodynamics, we can write delta Q is equals to delta U plus delta W. So delta Q will be equal to delta U plus work done can be written as P delta V. Now let us take the first case in which we are taking values at constant volume. So at constant volume, delta V will be 0. So delta Q will be equal to delta U. And Q can be written as Cv into delta T is equals to delta U. Here we have taken the value Cv because it is a specific heat at constant volume. So we can write Cv is equals to delta U upon delta T. Now in the second case, at constant pressure, delta Q will be equal to delta U plus P delta V. Now Cp can be written as delta Q upon delta T at constant pressure. That will be equal to delta U by delta T at constant pressure plus delta V upon delta T at constant pressure. Now for 1 mole of ideal gas, we can write ideal gas equation as PV is equals to RT. As pressure is constant, we can write delta V upon delta T is equals to R upon P, as R and P both are constant. So the Cp can be written as delta U upon delta T plus P into delta V by delta T can be written as R by P. That will be delta U upon delta T plus R. But from this equation, delta U upon delta T is written as Cv. So we can write Cp is equals to Cv plus R. So Cp minus Cv is equals to R. In all the equations in the derivation, the subscription denotes the quantity that are kept fixed. The Cv is equals to 1 upon n delta U upon delta T. It is true for all ideal gases, for all thermodynamic processes, even when volume is not constant. But for non-ideal gases, it is true only when volume is constant. The relation Cp minus Cv is equals to R is derived by using ideal gas model, but it is true within few % for many real gases at moderate pressure. For a few substances, Cp is less than Cv. Even if we are writing Cp is equals to Cv plus R, there are some substance for which Cp is less than Cv. There are some substances the volume of which decreases during heating. For example, water. The volume of water decreases between 0 to 4 degrees Celsius. In this case, delta W will be negative, so that heat input is less than that in constant volume case. That's why Cp will be less than Cv. Now let us see one example based on the relation Cp minus Cv is equals to R. Given the value of Cp is equals to 5 by 2R for monoatomic, we want to find the value of Cv. We know that Cp minus Cv is equals to R, so we can write Cv is equals to Cp minus R. So 5 by 2R minus R. So 5 minus 2 divided by 2 into R. So Cv will be equal to 3 by 2 R. From this knowledge, we can also find the value of gamma. Gamma is equals to Cp by Cv. That will be equal to 5 by 2R divided by 3 by 2R. So gamma will be equal to 5 by 3. Now, let us understand what are thermodynamic state variables and equation of state. Every equilibrium state of thermodynamic system can be described completely by some parameters or some macroscopic variables. These parameters or variables which describe equilibrium states of the system are called the state variables. The various state variables are not necessarily independent. They can be dependent on each other. So, the relation between the state variables is called the equation of state. For example, the ideal gas equation PV is equals to nRT. It relates three states, that is pressure, volume and temperature for any ideal gas. Thermodynamic state variables are of two kinds. First is intensive variables and the other is extensive variables. The intensive variables, these are the variables which are independent of size. That is pressure, density and temperature. The extensive variables, these variables, they are dependent on the size of system. For example, volume, mass and internal energy. Let us note that the product of extensive and intensive variables is extensive because it will become the size dependent. Let us understand a new term here, the isotherm. The pressure volume curve for a fixed temperature is called isotherm. That is, a graph for isothermal situation is called isotherm. Now let us understand different thermodynamic processes. First of all, let us discuss the quasi-static process, that is approximately a static process. Let us imagine an idealized process in which at every stage system is in equilibrium state. Such a process is infinitely slow, hence it is called the quasi-static. The meaning of quasi-static is it is nearly static because there is no temperature difference or there is no difference in state between two stages of the system. So it is called the quasi-static process. The system changes its variables so slowly that it remains in thermal and mechanical equilibrium with surrounding throughout. In quasi-static process, at every stage, the difference in temperature of the system and the surrounding is very small. The same is true for pressure difference between the system and surrounding. A quasi-static process is obviously a hypothetical concept. Practically, processes that are sufficiently slow and do not involve accelerated motion of the piston, and they also do not involve the large temperature gradient, that is large temperature change, are nearly approximated to be an ideal quasi-static process. So from now on we shall deal with quasi-static processes only, except when stated otherwise. If nothing is mentioned in the problem, then we will take it as a quasi-static process, that means the ideal process. So now, first of all, let us see the isothermal process. The process in which temperature of the system is kept constant throughout is called isothermal process. It is also known as constant temperature process. For a process to be isothermal, any heat flow into or out of the system must occur very slowly so that it always maintains thermal equilibrium. In general, for an isothermal process, none of the quantities delta U, delta Q or delta W is 0. All the values are non-zero. But in special cases, the internal energy of a system depends only on its temperature, not on its pressure or volume. The most common system following this special case is an ideal gas. For ideal gas, if temperature is constant, the internal energy is also constant. That is, delta U is equals to 0. And hence, the first law of thermodynamics then implies that given delta Q is equals to delta U plus delta W. For ideal gas, if temperature is constant, then delta U will be 0. So from this equation, we can write delta Q is equals to delta W. And from the ideal gas, PV is equals to mu RT. As temperature is constant, we can write PV is equals to constant. Now let us find the work done in the isothermal process. Consider an ideal gas enclosed in a cylinder with perfectly conducting walls and fitted with a perfectly frictionless and conducting piston of area A. Let its initial states be P1 V1 and final states be P2 V2. Here temperature is constant, let's say that is T. Now the force experienced by the gas will be equal to pressure into area. If we assume that pressure of gas during small displacement dx of the piston remains constant, then for small amount of work we can write W is equals to integration W, and integration dW is given by P dV, V1 to V2. But here pressure is not constant, pressure is also function of volume. So from ideal gas equation, PV is equals to mu RT. We can write P is equals to mu RT upon V. So W will be equal to integration from V1 to V2 mu RT upon V dV. Mu, number of moles, are universal gas constant. They are constant. As this is the isothermal process, temperature is also constant. So mu RT is constant. So we can write W is equals to mu RT integration dV by V, limits from V1 to V2. The integration of 1 upon V will be equal to ln V, limits from V1 to V2. So work done will be equal to mu RT ln V2 minus ln V1. Using the property of log, we can write W is equals to mu RT ln V2 upon V1. If we want to convert it into log, then we can write W is equals to 2.303 mu RT log of V2 by V1. So this will be the work done during the isothermal process. Now, as it is isothermal process, we can write PV is equals to constant. So P1 V1 is equals to P2 V2. So V2 by V1 is equals to P1 by P2. So the work done can also be written as 2.303 mu RT log of P1 by P2. The different graphs for isothermal process can be drawn by this. For PV diagram, isothermal process is denoted by this curve. For VT diagram, the isothermal process is denoted by this curve, and for PT diagram, the isothermal is denoted by the vertical line. This is the compression process. So this is the expansion process, and this is the compression process. So this is expansion, compression, and this is also expansion. Now, let us see the isochoric process. It is also called the isometric process. In isochoric process, volume will remain constant. As volume remains constant, work done, that is given by P delta V, is equals to 0, because as volume is constant, change in volume will be 0. So we can write delta Q is equals to delta U plus delta W. Delta W will be 0 because delta V is 0. So delta Q can be written as delta U, which is given by NCV delta T. So for isochoric process, delta Q is NCV delta T and work done is equals to 0. Let us draw various graphs for isochoric process. For PV graph, volume is constant, so this is isochoric process in PV graph. In VT graph, this is isochoric process, and in PT graph, a curve having constant slope can be the isochoric process. Next, let us see the isobaric process. In the isobaric process, the pressure remains constant. You can remember it like this: isobaric, bar is the unit of pressure. So isobaric process, that means pressure remains constant. So work done will be given by P delta V, that will be equal to P V2 minus V1. For ideal gas equation, we can write P V1 is equals to mu R T1 and P V2 is equals to mu R T2. So P V2 minus V1 can be written as P into mu R T2 minus T1 for 1 mole. Work done will be equal to PR into delta T. Now, delta U is NCV delta T. If we have taken mu is equals to 1, then delta U will be equal to CV delta T. So we have replaced P V1 minus P2, so this P will get cancelled out. So this will be R delta T. From the first law of thermodynamics, delta Q is given by delta U plus delta W. So delta Q will be, delta U is NCV delta T and delta W is NR delta T. Taking this delta T and N common, delta Q can be written as N delta T into CV plus R. But we know that Cp is equals to Cv plus R. So delta Q can be written as N Cp delta T. So at constant pressure, simply delta Q is equals to NCP delta T, and at constant volume, delta Q is equals to NCV delta T. Constant pressure Cp delta T, constant volume Cv delta T. Let us draw the various graph for isobaric process. First, we can draw the PV graph. This is isobaric expansion, and this is isobaric compression. On PT diagram, it can denoted by the horizontal line. On VT graph, it can be represented by a line having constant slope. Now, let us understand the adiabatic process. A process in which no heat transfer takes place between system and its surrounding is called an adiabatic process. That means delta Q will be equal to 0. Zero heat transfer is an idealization, but a process is approximately adiabatic if the system is well insulated or if the process takes place so quickly that there is not enough time to change the or exchange the heat. If delta Q is equals to 0, then delta U will be equal to minus W. Hence, we can see that the work done by the gas results in increasing internal energy. For adiabatic process of ideal gas, we can write PV power gamma is equals to constant. Here gamma is the ratio of specific heat at constant pressure to the specific heat at constant volume. Now, let us find the work done in adiabatic process. Consider an ideal gas enclosed in a cylinder with perfectly insulating walls, and it is fitted with perfectly frictionless non-conducting piston. Of area A. Let its initial state be P1, V1, T1 and final states be P2, V2, T2. Now, the small work done dW can be given by P dV. So, the work done will be equal to integration of P dV limits from V1 to V2. Now, as PV power gamma is equals to constant, we can write P1 V1 power gamma is equals to P2 V2 power gamma. So, work done can be written as integration dV upon V power gamma limits from V1 to V2. So integration of 1 upon V power gamma will be equal to V power minus gamma plus 1 divided by minus gamma plus 1 limits from V1 to V2. So work done will be equal to V2 power 1 minus gamma minus V1 power 1 minus gamma into some constant K divided by 1 minus gamma. Now, in the case of constant, we can write K is equals to P1 V1 power gamma, or K is equals to P2 V2 power gamma. So we can multiply this K and choose the value of K as per our convenience. So while multiplying with V2, we will use the value P2 V2 power gamma. And while multiplying with V1, we will use the value P1 V1 power gamma. So the work done can be written as P1 P2 V2 power gamma into V2 power 1 minus gamma minus divided by 1 minus gamma. This V2 power plus gamma and V2 power minus gamma will get cancelled out. So work done will be P2 V2 minus P1 V1 upon 1 minus gamma. P2 V2 minus P1 V1 can be written as NR T2 minus T1 upon 1 minus gamma. So this will be the work done by adiabatic process. Now let us see the polytropic process. For the polytropic process, the equation is given by PV power n is equals to constant. Let us find the work done in the polytropic process. The work done will be equal to integration of P dV, limits from V1 to V2. We can write P1 V1 power n is equals to P2 V2 power n. Let's say this constant is K. So W can be written as K divided by V power n into dV, limits from V1 to V2. So work done will be equal to V power one minus n upon 1 minus n, limits from V1 to V2 into K. So work done will be equal to V2 power 1 minus n minus V1 power 1 minus n divided by 1 minus n into K. Again, we can put the value of K as per our convenience. To multiply with V2, we'll put K is equals to P2 V2 power n minus P1 V1 power n into V1 power 1 minus n divided by 1 minus n. So work done will be P2 V2 minus P1 V1 divided by 1 minus n. So work done will be equal to P2 V2 minus P1 V1 can be written as NR T2 minus T1 upon 1 minus n. Delta Q can be written as delta U plus delta W. So delta Q will be N CV delta T plus delta W is NR T2 minus T1 is delta T upon 1 minus n. We can take this n delta T common. So it will be CV plus R upon 1 minus n. So from this we can write that specific heat for polytropic process is CV plus R upon 1 minus n. The cyclic process, a process that eventually returns a system to its initial state, is called a cyclic process. Since the final state is the same as initial state, the delta U will be 0 for the cyclic process. So from the first law of thermodynamics, we can write delta Q is equals to delta W for cyclic process. Every day, our body goes through a cyclic thermodynamic process. Heat Q is added by metabolizing food, and our body does work W in breathing, walking, and other activities. If we return to the same state at the end of the day, Q is equals to W, and the net change in the internal energy is 0. Let us see some examples. In a thermodynamic process shown in figure, given pressure at point A is 3 into 10 power 4 Pascal, volume at point A is 2 into 10 power minus 3 meter cube. Pressure at point B is 8 into 10 power 4 Pascal, and volume at C is 5 into 10 power minus 3 meter cube. During the process AB, 600 joule of heat is added, and during the process BC, 200 joule of heat is added. We want to find delta U for the process AC. Since internal energy is a state function, so change in internal energy during the process AC will be same as that during the process AB plus BC. So we can calculate the total work done delta W during AB plus BC and total delta Q during this process. Then we can find the delta U. So let us process. First we can write delta U from A to C is equals to delta U from A to B plus delta U from B to C. Let us find the work done for AB. That will be 0 because the volume is constant, and work done during BC will be equal to PVC minus VA. Pressure at point B is given 8 into 10 power 4. Volume at C is 5 into 10 power minus 3 minus 2 into 10 power minus 3. So 8 into 10 power 4 into 3 into 10 power minus 3. So that will be 240 joule. Now delta Q is equals to delta U plus delta W. So delta U AB is equals to delta Q, heat added in AB is 600 joule, that will be positive, minus delta W. Delta W for AB is 0. So delta UAB is 600 joule. Now delta UBC is equals to delta Q for BC is 200 joule minus 240 joule is equals to minus 40 joule. So total change in internal energy will be delta UAC will be equal to delta UAB plus delta UBC. Delta UAB is 600 joule plus delta UBC is minus 40. So the change in internal energy during process AC will be equal to 560 joule. So this will be the final answer. In this example, heat is supplied at constant pressure to diatomic gas. The part of this heat which goes to increase its internal energy will be delta Q for constant pressure is given by NCP delta T, and delta U is given by NCV delta T. We want to find the part of heat that goes into change in internal energy. That will be given by delta U upon delta Q. So NCV delta T upon NCP delta T. So delta U upon delta Q will be equal to CV upon CP, as this is the diatomic gas. For diatomic gas, Cp by Cv is equals to 7 by 5. So Cv by Cp will be equal to 5 by 7. If we have been asked that the part of heat that goes into work done, so we would find delta U upon delta Q, that will be equal to 1 minus 5 by 7, that will be equal to 2 by 7. In this example, 70 calorie of heat is required to raise the temperature of 2 moles of an ideal diatomic gas at constant pressure from 30 degrees Celsius to 35 degrees Celsius. The amount of heat required in calories to rise the temperature of the same gas through same range at constant volume is, at constant pressure, delta QP will be equal to NCP delta T, and at constant volume it will be NCV delta T. Taking the ratio, delta QP is given 70 divided by delta QV is equals to CP by CV. It is diatomic gas, so CP by CV will be equal to 7 by 5. So delta QV will be equal to 70 into 5 divided by 7. So delta QV will be equal to 50 calories. So this will be our final answer.